Okay, let's start the second part of lecture today. We're going to solve more example. Okay, so we already worked on F10-9, and next one F10-10. Obviously, there are so many problems here. We just quickly go over most of them. So F10-10, you have, it says determine the angle of twist of the wheel B with respect to A. Let's zoom on it. Okay, more. So the shaft has a diameter of blah blah, made of steel 4G. Alright, so basically what it asks for is, let me draw here, the angle of this wheel with respect to this one. So it's not talking about none of this bearing here. Okay, so what we need to do is to have kind of torque diagram between these 2 points. And as you can see, this system, the summation of forces, if I put the axis here, let's say this is x, and then y, and then z, and you can easily see that the summation of forces in the y direction is naturally 0, but the summation of force in z direction is not 0. It's equal to 1 4k plus kk in 10k in the negative z direction, and it's like 14k in the negative z direction. So then you can see that this bearing right here, they are here for a reason, because they can counter the effect of summation of force in z, make all 0, so such that this system remain in equilibrium. Similarly, in the x direction, summation of forces in the x direction is 6k negative 2k is negative 8k. Therefore, there should be 2 components here in the x direction to counter this effect and keep the system in equilibrium. Similarly, for the moments, because it's a three-dimensional object, we have 3 equations for summation of force in x, y, z0, and also 3 equations for summation of moments in 3 directions 0. As you can see, the summation of moment, let's just consider summation of moment in the y direction. So I'm going to write it here, summation of moment in the y direction must be 0. If I sum them up, I'm going to get 1 4k. Let's start with the 4k. Let's see if I can reduce the thickness of my pen. Obviously, yes, I can. So if I expand these equations, let's zoom a little bit more, because I need more space to write. It doesn't zoom more. I need to write 4k times the moment arm, which is 100 millimeter. This is negative. Then I go to the other 10k, is 10k times 100, and this one is positive. Then I go to 6k times 150, and this is negative, and then I go to 2k times 150, and this is all the moment, the external moment that I have on these 2 wheels. And I know there are some moments, one here and one here, but assuming that these are journal bearings, that means there are ball bearings here. They don't actually add any friction or any kind of moment that gets the shaft engaged. So we hope that the sum of this should naturally go to 0, so we don't really need to take care of this effect of bearings here. That's what I'm trying to reach to. So if I put this in the calculator, I'll see, let's put it in the calculator, negative 4k times plus 10 times. Yeah, it adds up to 0. So what I do, I say, well, all I need to find the moment distribution between from starting from here and ending to here in this section, right? So what I'm going to do, I'm going to cut a section here just like I did it before, and assuming that my x is, let's start from here, from the wheel A. This is your x. Then I make a free body diagram to see how much moment I have from point A to B, right? So what I do, I just make it here two-dimensional version of this two-dimensional object. This is A, and this is B, and this distance is 450 mm, and my x start, let's see if I can get another color. Yeah, my x start from here, and I need to refine this a little bit. Yeah, my x starts from the left, and that's all I take care, because I don't care about this bearing. As I said before, I mentioned the reasoning for that. So if I do that and I create a FVD, then I realize that the FVD is going to be, so this is my cut. So you're going to have a positive moment, which is this way. It goes to positive y, m at x. And here, on this system, you have a 4K times 100 mm this way, and the opposite 6K times 100 mm the other way. That's all you have for your system, assuming that that's a journal bearing on this point, right? So if I sum up the moments, then I get summation of moments. Let's write here summation of moment. About y-axis should be 0. Then you get mx, which is a positive one, negative, let's write it here, if hopefully I can drag it, yeah, negative 4K times the distance 100 10 to negative 3. So 4K times 100 10 to negative 3 with the negative, plus mx, and finally I have a positive 6K times 100 10 to negative 3 is equal to 0. So my moment at x is equal to, put it in calculator. So obviously this is 6 minus 4, 2K times 100, the K cancel out with this K. So it's like 200, take it to the right, negative 200 Newton meter. Double check, put it in calculator. Yeah, negative 200 Newton meter. Therefore, when I use the equation that I obtained in the class, that phi is equal to TL over GJ, okay? Then I substitute for the torque from here to here in this region. I substitute the negative 200 Newton meter times the L, which is 450 10 to negative 3, divided by G 75 to 10 to 9 is giga times j pi over 2 whatever radius is. Let's see what the radius is. Radius of the shaft. It says shaft has a diameter of 40, so the radius is 20 millimeter, 10 to negative 3. Don't forget the 4, and that's it. So you put it in a calculator and you obtain the final value. Don't forget that this is going to be in radian. Then if you want, you can convert it to degree to get some feeling about it. The rest, okay, let's talk, work on this distributed load. This is similar example F10, 12, similar to what we had before. 10, 13, say 80 millimeter diameter shaft is made of steel, subject to uniform distributed torque. Determine the angle of twist at the end A, take G. Okay. So basically what it does, it says you have a 5 K Newton meter per meter of torque at any section here. As you can see this, I'm talking about this. 5 kilonewton meter per meter. So it's a constant distributed, it's not a point couple moment, it's a distributed couple moment. It's analogous to the distributed force. And what we need to do, we need to find, obviously point B right here is fixed to the wall, so it doesn't have any twist or rotation. But point A here, it will have a rotation. And if we take this axis X positive, obviously the rotation is in the positive direction, obviously, because the distributed torque is in a positive direction. So all we need to do is to substitute in the formula that we had before, and the formula was integral T dx over Gj, I think, if I'm not, yeah, T dx over Gj. So Tx, where is the eraser? Right here in this software. This is a cool software, I like it. Tx dx G at point X, J X, from 0 to L, which is here 800 millimeter, and this is your torque. Now all we need to do is to substitute the T, G, and J, and make sure if they're variables, substitute here a function of X. So I take my X starting from here, this plate, so that's my X. If I cut it somewhere here, this cut plane, so that's your X in 3D. It's like that. Obviously T at X is equal to 5K times X. Why? Because look at here, it says 5K, I'm talking about this part. Do we have highlighter here? It says 5K Newton meter per meter. That means if I consider the X for X meter, then I have to multiply by X to get rid of this meter right here. You see that? So I multiply by that. So that's my T of X, and now G of X is constant, J of X is constant cross section. I just put it here and take the integral. So that phi is equal to 0 to L. L is 800 millimeter converted to meter. Don't forget everything we do, meter, Newton, and radian. If you have degree, you have to multiply by pi over 180 before you substitute in the formula. Don't forget that. So from 0 to 0.8, T of X, which is 5 times 10 to 3. Look at this K. This is one of the most problematic part. Not great. They forget to put that K here. So that means 5 times 10 to 3. Don't forget the X. So that's your T of X, right? Highlighter. We're talking about that. Then you multiply by dx over g of x, which is 75, highlighter, right here. I got it from here. You see that? So 75, and it's a giga, so 10 to 9 times j of x, and j of x is pi over 2, whatever the radius is, and the radius is 40 millimeters, so 10 to negative 3 meter to the 4. So obviously, if I want to take this integral, I can take, again highlighted, I can take this constant, and this constant, and this constant, I can take it out, and the only term that remains inside this integral is x dx. Okay, so if I do that, I get 5 10 to 3 divided by 75 10 to 9 pi over 2 40 10 to negative 3 to the 4. You see, I took everything out, and this is going to be, this integral, another color, this is going to be x2 over 2. So I just do that, and then the final result becomes 0.82 over 2. That's it. You just put it excuse me. You just put it in calculator, and you get the numerical value. All right, so let's go to the next example. So this is like one of distributed load we solved in the class, this example. Next example, let's work on this one. Let's work on this example right here. Let's say a 30-second steel shaft has a diameter of 50 millimeter and is subject to distributed load, which is 200 Newton meter and 1 concentrated load. So again, highlighter, we have one concentrated load here, a point load, which is point torque, so it's 250 only at point C, right? And there is another torque, but this one is distributed. Look, this one that I'm highlighting, this one is not at a point, it starts from A and ends at C, and it says determine the absolute maximum shear stress in the shaft and plot the graph of angle of twist in the shaft value versus x. Okay, so again, we know that the maximum shear stress, or shear stress in general, is equal to, due to torsion only, is equal to T over J times R for a constant for a part of the beam or shaft that has a radius of R. So at any location, let's zoom on it a little bit. Yeah, so at let's say this element is right here, and this is located at the distance of, let's use turquoise and make it finer. Yeah, so this element is located distance R from the center, which is in this case of torsion, the center, the line passing through the center, is our neutral axis, because the shear stress is 0 there. Let me show that. So this is the neutral axis. This dashed line is the neutral axis. So the shear stress at the very center is 0. So with the distance R from the center, this formula, we showed it in the class, T over J times R is the shear stress at any location. So the maximum of this happens when R is equal to the radius. So the formula that I have is T over J times R, tau max. And you can see that the very max, tau max, the global max, it happens when you reach to the maximum torque over J minimum times R maximum. By simple, you remember we did high-low? The top should be max, the bottom should be min. This similar thing like that. So we know that here, this term, highlighter, this term is just constant. So we just simply say J, because the radius is constant across the shaft. If you have a shaft that is composed of different cross section, you have to find the minimum, right? And you have to check if this tau max is happening in that minimum. So the combination of this matter, right? So in this case, our job is simple, because J min is simply J, which is pi over 2 radius to the fourth power. So all I need to analyze this problem is distribution of tau, or the torque, actually T, not tau, or the torque, to find the maximum. So in order to do that, I realized that, well, from here to here, we need another color here, from here to any point here, let's take it X, the torque is just constant, but it's a distributed load. Like example before, I can write tau is equal to 200 times X. So what's the maximum of this when we reach to X is equal to, so this value between 0 and 0.5, before 0.5. 0.5 is singularity, okay? So if I put 0.5 there, then I get half of 200 tau due to this constant load is just 100 Newton. This is actually T, not the stress, T, the torque distributed couple moments, right? So it's 100 Newton meter when we go to the X is equal to 0.5. Okay? And it is the other way. It's like this way. You see that? And then immediately after that, we have something that is going to 250 this way. So they kind of cancel out, and then we have a remaining 150 in this region. If the wall torque is 0, assuming the wall torque is 0, this is all assuming the wall torque is 0. But the wall torque may not be 0. So all I need to do, back to the main point, in order to find that, I need to draw my torque diagram before I even start solving this problem. So in order to do that, I just simply make a FVD. So I say, let's take your positive, X positive here. You can, excuse me, you could take positive, for example, in other direction, like this way. It all depends on which way you want to go. But I don't do that. I just take it this way, right? And then I make FVD. Don't forget the 5 steps you have. So you have, this is your system. The wall torque, you don't have it, but you put something in a positive default direction, and you put a symbol. So when we solve some equilibrium equation, we will find it. And then you're gonna have a distributed torque here, which is 200 times X. And then there is going to be here 1 point torque, 250, and then nothing else. So this is your FVD. Okay? So if I write summation of torque in the X or moment, both are same. Sometimes we call torque, sometimes call it moment. In X direction, you see this positive X is equal to 0. Then I have to say MA, positive, negative, summation of all this 200X from, so you can say summation of 200x from 0 to 0.5, okay, plus 250 is equal to 0. So what happened here? Look at this term. This is just simple summing up. If I write here, summing up all these little delta torques coming from this distributed torque here, starting from point 0, x0, and ending at point x is equal to 0.5. So I wrote it as an integral, 0 to 0.5, and the magnitude was 200x, and there is a dx here, right? It's just simply summation of torque in this area, in this region. And because the direction was negative, I had to include a negative sign here. But for 250, I had to include a positive because it's 250, you see, use your right hand, you see this 250 is going to the right direction. So that's the reason I have a positive here, is equal to 0. So then I solve this for MA. So let's compute this integral. MA, negative, this is going to be 200 times x2 over 2, which is x 0.5 2 over 2 plus 250 is equal to 0. So if I put in the calculator, then I get 100 times, this is going to be, take it to right side, half of 200 times 250 is equal to, MA is equal to negative 225 Newton meter. So that's what I have here. Right here at the wall, I'm gonna have something. Let's use another color. Hopefully, I need a green here, darker green. No, not darker green. Yeah. So at the wall, I'm going to have a couple moment that is like that. It's negative. It's positive to the right, negative that way, and its value is equal to 225 if the integral and calculation is right. Right? So I go ahead and draw my moment diagram. I wish I had more space. Can I have more space here? Yeah, I think I have. So if I draw the moment diagram, then I know that I have to do two cuts from A to C and then from C to B. From A to C, let's do that. If I cut it, use black, from A to C, then I'm going to have 250, 225, this coming from wall at x0, and it's negative, and then I'm going to also have a distributed one which is equal to 200x, and this is my x that I cut. And here at this location, I'm going to put 1 this way, m of x, the internal torque. That's what I need in order to substitute into my tau max is equal to t over j times r. So excuse me. So let's do summation of moment x0, equilibrium equation. Then I get mx positive negative 200 times x and negative 225 is equal to 0. Then that's going to be mx is equal to 225 plus 200 times x. This is my internal torque, is a line, is not a constant value. So if I want to make a plot for that, torque versus x, This is X, point C, point B, and point A, and tau of X, T of X, or torque internal. Okay, then I'm gonna have a line. So what is the value of that when X is 0? Is 225. Okay, so this makes sense because the external was negative 225, but the effect on internal becomes the opposite according to Newton's third law. So I put here 225 when X is 0, and when X is equal to 0.5, then I get 225 plus 200 times 0.5, then I reach to this point, and this value is 325, 300. So 225 plus 200 times 0.5, which is equal to 325. Okay, so this is it's a positive, internal torque is a positive distribution of internal torque. Now I'm gonna go and cut it from point C to B. I can take either from the right or from the left. So if I take it from the left, my system is going to be like this. So this region, first of all, I have a negative 225 external, and then I have a distributed load from point A to C, and its value is equal to 200 times X, and I know the integral of that, the summation of that is integral 200 X dx from 0 to 0.5. Okay, and this value is negative. And then I have a 250 this way, and when I cut it here, then there is going to be also mx this way. So compare it with the case, this is part A, when I had to cut it between A and C, and now this is part the second cut from C to B, which I had to include mx at the location x. So from here to here is still x. Okay, so let's do summation of moments about Ex. Summation of moment about the x must be 0. Then I get negative 225, again another negative, integral 0 to 0.5, 200 x dx, this term, right? Then plus 250 plus mx is equal to 0. Now solve for mx. This one is equal to this integral, negative 225 negative 200 times x squared over 2, which is 0.52 over 2, plus 250 plus mx. So let's put it in calculator. Negative 225 negative 0.5 times 200 times 5x squared plus 250 is equal to 0. Interesting. So the mx became 0. Let's use a good highlighter here. Look at that. Beautiful. Why mx is 0? Can you say that? Just pause the video and think about it. Now, assuming that you already paused the video and thought about it, the answer to that is, what if you cut it from right? Let's call it x bar. If you cut it from right, you see this part is free in space. right? It's not engaged, so the moment should be 0. So my couple moment distribution from C to B is what? Let's emphasize. It's a fancy color here. There you go. It's 0. What does it mean? That means when I go to the diagram here, from here to here, the couple moment is 0. So what do you see? Where is the maximum couple moment? Internal torque. Where is the maximum? The maximum is right here. 325. And it happens just before point C. You see? This is like mathematical abstract. You remember we had negative, positive, just before, just after. It happened just before point C. And its value is 325. Now when I want to solve this problem, all I need to do, going back to the main formula, can I have a highlighter of different color? Like purple. There you go. Instead of T, I should substitute 325, right? And it's going to give you the maximum. So let's do that here. I'll just put 325, and J is pi over 2. Radius, what is the radius here? The radius is 25 millimeter. 4 times another radius here, 25 10 to negative 3. So that's what you get, the maximum shear stress. And where is the location? Now that this is one thing that I add. I said determine the location of this when a maximum shear stress happens. And the location is, let's use another color. What color we haven't used yet to distinguish it? Maybe, no, this is maybe, let's see, this kind of blue. We haven't used that. So it happens right here. Oh, that's not going to work. It happens right here. See the maximum on the surface of this shaft at point C minus. That means right here, just before point C, at the surface of the object. Okay. Now, also it may ask, okay, draw, find, for example, deflection of, or in this case of torsion, the deflection is the twist or rotation angle. Find the rotation of point B with respect to A. Well, all we need to do is just to find this integral. So if I find a little bit more space here, phi of point B with respect to A is equal to integral A to B tau of x ex over gx jx. Good news is these two are constant, right? Take it out. 1 over g times j, which you already know the values, integral from A to B dx. And now all you need to do, what is that? Tell me what this thing is. This thing is the integral of the torque diagram versus x, which means the area under this curve. Let me show that area with another highlighter. Maybe what kind of color? Pink. So this is this area. It is 0, no area here, and then the area of this, which is the area of this trapezoid. And so you add 325 plus 225 divided by 2 times the height, which is 0.5. So you put it right here instead of this ugly term. Then you divide by g over j, and you find the angle of twist of B with respect to A. So more example here. Again, these are all similar to what we have solved. 1010, 1040, 1041, 1040. It's just they change a little bit of the flavor what you need. For example, this example practical deviation used to mix the soil in order to provide the stabilization. Okay, they used to make diameter is given, this one the angle of twist. Well, this is just very obvious. You see this area, I mean, you don't need to think about this complicated shape, right? All you have is a simple, let's use a this simple shaft here, and it's fixed to the one end, and then you have one torque here and another torque here, and we already saw lots of examples like that. Okay, so this one is also nothing new. You have some sort of distributed load, 1 2 plus 1. Do we have a point load here? No. Two distributed loads, opposite direction. So one is like 500, negative 500x. The other one is 1000, positive 1000x. But don't forget, whenever you take the x, you have to take, for example, the same location here, x reference, and then we have exactly the same problem we had before, even simpler. Again, these are the same problem here. The torque, let's read it. This is inside the turbine that is used in the power plants and lots of other places. A 6-inch diameter steel shaft and turbines of Jordan. Alright, 0 to 200 pounds a D. So the torque here is the distribution of the torque. You remember we had something like constantly distributed torque, and it was like 200x. But here it says the torque, let's use the eraser, the torque is linearly changing. That means the torque is 0 here. I need a little bit thicker, maybe a better color also. What color we need here? Maybe red, a little bit thicker. Yeah, the torque is 0 here, and it reached to a maximum at this point, and the maximum is 200 pound-feet here, and it's 0 here. 0 at C and 200 pound per feet. So if you write T of X, you write 200 times X. Let's see, I'm making some mistakes here. It reached 200x here and 0 here. Yeah, so let's see. When the torque is constant, like that, this should be 200 times. Let me think about it. This is, I'm not. This is, it says turbine blade creates a torque on the shaft increase linearly. Yeah, this is correct. This is the linear starting from 0 to 200. But the one that we solve here, let's see, this, the one that we solve here also is 200 times x. Even if it's constant, when you multiply by x, okay, sorry, this is right, because it's constant. Look at here, we need a good marker, here, red. So look at this term, 200 in red. So in fact it says it's constant 200, but when because it's Newton per meter, then you have to multiply this by a meter to get rid of the meter at bottom. It's Newton per meter times meter, right? You have to, times Newton per meter by meter. Then you have to multiply this by x, in order to get rid of this meter at bottom. That means that even though this was 200 constant, I had to multiply by x to get rid of this meter in the bottom, to get pure torque, not torque per unit length. Now here, let's go back to this example. The turbine, you see the torque by itself is 200x per location. But look, what is the unit of that? Let's write the unit of this here. The unit of this is Newton per meter divided by meter. That's the unit of this distribution that I write here. Now, in order to get rid of this meter in the bottom, then you have to multiply by an x, another x. So in fact, your real equation becomes 200 x squared t of x. Now when you plug in the formula, what do you get? You get the angle of rotation b with respect to a is equal to integral from a to all the way to b, right? T of x dx over gx jx. Now you can say this integral is equal to integral from a to c. From there to there, t is constant. You have to find this TAC. You can easily find it with the equilibrium equation. Times LAC, which is 2 feet, divided by GJ, which is constant for the entire thing. So you can simply take this guy out. So let's bring it out here. 1 over GJ plus integral from a to b, t of x, integral from c to b d, to b d, not b, to the d. What point do I took? To the d. Let's take it to the d of t of x. Now you put t of x, which is 200 x squared dx, and gj we already took it out right here. So that's it. Plus integral d to b, and right here is torque from d to b divided by, multiplied by L, which is simply 2. Here from here to here is also 2 feet. And you can also find this from equilibrium, assuming this frictionless journal bearing. So you have this. These are simple thing. One equilibrium equation. This integral is simply 200 times x3 over 3 from 0 to 10 feet. Another color from here to all the way to here, right? And then when you do that, you substitute the value, you find the relative angle of deflection. Similarly here, the torque, look at here, the torque is kind of parabolic x squared, but it also has a constant here. In the previous example, it was parabolic, right? So what can I do here? I just simply write this integral and use the black color. So I say phi, the rotation of A with respect to B is integral x from 0 to x is equal to L t, which is t0 times 1 plus x over L square dx over gj, g and j, and j is simply pi over 2 r force. Then you can take this guy out, take it out, t0 2t0 pi g r to the fourth power, and this integral 0 to L 1 plus x over L square dx. And this integral is pretty easy. What is it? You get 2t0 pi g r to the fourth power is equal to L